Alright, so we're going to go over this FRQ. So, in this FRQ, it gives us the reaction, and then it starts asking the questions. Now, if you have an FRQ where it gives you a long prompt in the very beginning, skip it and then go directly to the question and then go back to the prompt to see what information you need to get from it. For this one, the first question says, determine the oxidation number for the chlorine, NaOCl. Alright, so sodium is going to be a +1. Oxygen is not in a peroxide here, so it's -2 like it normally is. So that means everything here needs to add up to 0. So this has to be +1. So in this case, the chlorine has an oxidation number of +1. Alright, calculate the number of grams of sodium thiosulfate needed to prepare 100 milliliters of a 0.5 molar solution. So this is a simple conversion. So you're going to start with your volume, you're going to use your molarity to go to moles, and then you can go to grams right after that. So you have 0.5 moles for every 1 liter, and then you have 158.10 grams for every 1 mole. All right, and then you're going to do the calculation. You should get 7.90 grams. And also make sure you're paying attention to significant figures. We have 3 significant figures here, so you should have 3 here. All right, so the next question, it gives you a data table. It says, using the balanced equation for the oxidation reduction reaction and the information in the table, determine which reactant is limiting. So if you look right here, all 3 of these are reactants. It gives you the same concentration, it gives you the same amount. So really what matters here are the coefficients. So if you wanted to, you could simply go ahead and calculate moles of any of the products, and then you would be able to figure that out, which one produces the smallest amount, or you could just simply think about it because you're given the same amount and same concentration for everything. So really it's just going to depend, okay, on the coefficients here. So it takes 1 of these, 4 of these, and 2 of these for every time you have the reaction. So that means you need more of the sodium or the NaOCl than you do of the other 2 reactants. So if you're starting off with the same exact amounts and concentrations of everything, that means that NaOCl has to be the limiting reagent. So you could have done this 2 ways. You could have done the calculation and shown it, and that's fine. Or you can just simply say, well, it's going to be this because you have the same starting amounts of everything, and it takes 4 of these for the reaction. It takes more of the NaOCl than it does of the sodium hydroxide or the Na2SO2O3. So now let's look at the graph. Okay, so the solutions, all originally at 20 degrees Celsius, are combined in an insulated calorimeter. The temperature of the reaction is monitored. So it's showing you the temperature change as the reaction progresses. And the next question says, according to the graph, what is the temperature change of the reaction? So if you're starting at 20, you need to go to the graph and make sure you're looking at the highest temperature here. And it's 32.5 roughly, because that's 33, so that should be about 32.5. So 32.5 minus 20 will give me 12.5 degrees Celsius. All right, so now, the mass of the reaction mixture is going to be 15.21. And then the next part of the question says, calculate the magnitude of the heat energy in joules released during the reaction. And it gives you a specific heat capacity of the reaction mixture, and then we don't need to worry about the container. So we have specific heat capacity, we have a mass, we have a delta T because we just did that, and D, so that means we're going to be using Q equals MCAT. So Q is equal to 15.21 multiplied by the specific heat capacity multiplied by my delta T of 12.5. So my Q here is going to be equal to 749 joules. Okay, so essentially what happens is we've taken those three reactants and the first page and we have put them together. The temperature did go up. It went up by 12.5 degrees and then it released 749 joules during that reaction. All right, so now using the balanced equation for the oxidation reduction reaction, it wants you to convert it into kilojoules per mole. Okay, so we have joules, we've got to get that into kilojoules, and then we've got to divide by the number of moles of our reactants. All right, now, first thing, let's go ahead and convert that into kilojoules. So that's going to be 0.749 kilojoules. That's the easy part. Now we have to deal with the moles. So the thing is, okay, don't start with this. This is of the reaction mixture. That's of all the reactants. So go back and look at the information given to you here. Okay, so, and the first part of the question, it asked you, what is a limiting reactant? Well, it's NaOCl. Okay, the amount of heat that's produced in this reaction is going to depend on the limiting reactant. So they had you find the limiting reactant in the first part because you're going to need it in the second part. You have to use the amount of moles of the limiting reactant here. So you have 5 milliliters, so 0.005 liters. The molarity was 0.5 moles per liter. Okay. And then in your reaction, okay, for every 1 mole of reaction, you had to use 4 moles of the reactant. So if you go back and look at the reaction, remember there's 4 moles of that. So whenever this reaction occurs and it releases so much heat, you need to have 4 moles of that to produce that amount of heat. So essentially, you need to account for that in your calculation. So I'm going to get 0.000625. Okay, so that's how many moles. And then your kilojoules would be 0.749 kilojoules divided by this. So you're going to get 1200 kilojoules per mole. However, you need to think about this. So the temperature did go up. Okay, we measured the temperature change, and that's the water in the solution. So if the water absorbs energy, this has to release it. It's negative. So there is a point in the score guidelines that says that you need to have that negative sign to get the third or the second mark or the second point. Okay, so when you're doing a problem like this, make sure you're accounting for the coefficients, okay, because it takes 4 moles of that limiting reactant to make whatever the amount of energy is. So you have to account for that in your calculation. All right, let's look at the next part. Okay, it says the magnitude of enthalpy change in kilojoule. Okay, so we did another experiment essentially. They doubled the amount. So they haven't doubled the concentration, but they doubled the amount of the reaction. Well, if that were to happen, I would probably expect maybe more heat to be released. because you have more of the limiting reagent. However, it's asking how this would compare with the calculation that we just did, kilojoules per mole. Well, this is a ratio. So kilojoules per mole, that shouldn't change. The amount of heat energy that you release, if you have more, yeah, you might get more energy, but you're not changing that ratio. The kilojoules per mole should still be the same. So the kilojoules per mole should be the same. The heat released may be more. All right. All right, so when we're looking at writing the net ionic reaction here, essentially what you're doing is you're getting rid of all the spectators. So anything where the oxidation number doesn't change throughout the entire reaction can go. So sodium's oxidation number is going to be +1 throughout this entire thing. Now, once you get rid of that, what you're left with is this, and then I have that. This, that, and then I also have my water. Okay, so molecular items cannot be broken down. So even though oxygen's oxidation number isn't really changing here, you're not going to get rid of it because it's attached to something. So it's going to stay there. Now the sodium throughout the entire reaction is +1. It's +1. It's +1. It's not attached to anything else because remember, you take an ionic compound, you put it into water, the ions split. Now this will not split because it's molecular. Okay, polyatomics are molecules. You don't break those up. So really, sodium is really the only thing that can be left out of the net. So let's just go through and make sure we have the proper number. It should be 4 of these, 2 of those, 1 of those, 4 of these, and 1 water molecule. And then that's really your net right there. So all you've really done is you've just taken out the sodium ions.